Oh yeah, the light is blinding. Hi, my name is Subodh Iyengar. I work on the transport security team at Facebook. So my team primarily focuses on encrypting data in transit and making that encryption as fast and secure as possible. So today I'm going to talk about zero round-trip security protocols, primarily our experimental protocol called Zero Protocol, as well as TLS 1.3. So I have a bunch of stuff I want to cover to this presentation. So a quick overview, I'm going to cover the TLS protocol, a quick overview of that. Zero Protocol, which is our experimental zero RTT security protocol, why TLS 1.3 is different from Zero Protocol, and why we're moving from Zero Protocol to TLS 1.3. Spoiler alert, zero round-trip protocols are not free. I'm going to try and cover some of the challenges that we faced while deploying and implementing zero RTT protocols. And I'm going to cover our own implementation of TLS 1.3 and our experiences deploying TLS 1.3 to our production servers. So quick overview of TLS protocol. TLS is the de facto standard for encryption on the internet. It is used by Facebook and various other companies to encrypt traffic, both externally as well as internally. So it provides many useful properties for security encryption. It provides secure parameter negotiation, so you can exchange things like cipher suites without man-in-the-middles being able to downgrade your connection. When you talk to another service using TLS, you know exactly who you're talking to. So no man-in-the-middle can tamper your connection. So TLS, mostly the way it's used at the connection level. So when I establish a TCP connection to a server, I first make one round trip for the TCP handshake. Then the TLS layer comes in and does one round trip for SSL key exchange. It should be updated to call TLS, not SSL anymore. But after this keys are exchanged, each side has keys to start encrypting data and sending application data in transit. So really, the key TLS adds one round trip to the connection establishment of whenever you establish a connection. So we've done a bunch of stuff to speed this up in the past. We've deployed an edge network, which puts servers closer to the users. We use the standard techniques like false start, ticket resumption. But at the end of the day, TLS still requires a minimum of one round trip to establish a connection. So this adds some overhead to establishment of the connection. So when we were looking at this about 2 years ago, at our data that we had from mobile clients, we were wowed. Wow. For example, in 2G networks in India, it takes about 600 milliseconds to 1.9 seconds at 75th percentile to establish a connection. So these are real latency numbers which affect the user experience. So one of the ways to ameliorate this connection setup cost of TLS is to reuse connections. So even in emerging markets, we see that the connection reuse rate is much lower than in the rest of the world. So we wanted to do something about this. How do we fix this problem? So in Facebook, we're in a unique situation where we control both the client and server, which is the client being our mobile apps and our load balancers. And we not only control the clients and servers, we also control the implementation of the networking stack as well as the load balancer as well. And they're both built on the open source Proxygen library. So it's a cross-platform implementation. So we decided, hey, can we experiment with something that makes the handshake zero round trips? So we decided to do some experimentation on zero round trip protocols. When we were looking at what to do, which implementation, which protocol to use about 2 years ago, there were several options for us to choose from. There was obviously TLS 1.3, which wanted to do zero RTT, but at the time, it was really in the nascent phases. It didn't really have zero RTT support at all in the specification. But there was another effort, parallel effort going on at Google to deploy a protocol called QUIC. QUIC is a completely zero RTT transport protocol, and it has its own cryptographic algorithm, which supports zero RTT. So we wanted to kind of play around with this idea of zero RTT security without completely overhauling our infrastructure. So what we decided to do was build Zero Protocol. So Zero Protocol is, next slide. Okay. Zero Protocol is our own experimental zero RTT protocol. So we built this over the last few years. It's based on QUIC crypto, but it's actually built over TCP. So it has a bunch of changes to make QUIC actually much more secure. So I'll talk about that briefly. And it also adapts QUIC's crypto to run over TCP as well. We've actually since then deployed this and implemented it in both our Facebook for Android apps and Facebook for iOS apps. And so if you're using one of our apps, you're probably using Zero Protocol to communicate with Facebook right now. So what makes Zero round-trip exchange possible? Really, the central idea of Zero Protocol is, and Quick itself, is that you have a data structure called the server configuration data structure. So this contains most importantly, a field called the static public key. So this is a Diffie-Hellman key share, which is hosted for a certain amount of time on the server. So let's say a client has never communicated with a server before. So the client who has never communicated with a server before needs to do one round trip to go and get that server config. So there's still one round trip involved with the Zero RTT protocol. But once it's got that server config, it actually ends up caching it locally and storing it for later use. So if a client has talked to a server before, it knows about this static public key that the server has advertised before. So when it starts up a connection, it derives a new static share, new ephemeral share for the client. It does a Diffie-Hellman key exchange with the server static public key and derives something called zero round-trip keys. So these zero round-trip keys are important because now you have something to encrypt this initial app data with. And the previous connection, you had to wait for the server to exchange keys and get these keys to encrypt the data with. So in the same flight, you kind of you encrypt this zero RTT data and you send it over, and great, now the server gets a request and it can process this request. So the server derives now a new Diffie-Hellman key share. And then it does a key exchange with the client key share, and it derives a new set of keys called the 1RTT keys. So this is really important in zero round-trip protocols, where you have this difference between zero RTT keys and 1RTT keys. When the client receives these 1RTT keys, it can start sending data encrypted with the 1RTT keys. So it latches on to this 1RTT. So at a high level, if you look at the 1RTT versus 0RTT flow, so at the left, it's TLS 1.2, the older version of the protocol, and the right is Zero Protocol, where you see that the client had to wait for the server to respond before it could send the application data. Versus in Zero Protocol and Zero Round-Trip protocols, the client can send the data on the same flight as the handshake. So that's what makes it Zero Round-Trip specifically. Great. So we deployed this in our Android and iOS apps, and we got some really awesome results from it. As expected, we saw our connection times go down by about 41%. Our total request times go down by about 11%. And overall, including connection reuse and resumption, we saw this go down by 2%. Now, you might think like 2% is not a big number, really. Like, you did all this work for 2%. But you have to remember that all requests are not really created equal. So for example, when you start your app, you have no chance for using a reused connection at all. So Zero Protocol really speeds up those requests and results in increased user engagement. And in other situations where you switch networks and stuff happens in mobile networks, towers fall over. So it really resulted in increased user engagement when we deployed this thing. So next we'll talk about TLS. Why is TLS 1.3 different from Zero Protocol? And why are we even doing TLS 1.3 in the first place? Why is the community building TLS 1.3? So the last version of TLS, which is TLS 1.2, was released sometime in 2008. A long time has passed since then. And over the years, many, many attacks have happened over TLS. So some of them have cool logos, some of them do not. So I was liberal enough to make up cool logos for the attacks. Sloth, poodle, all this other stuff. So TLS 1.3 had many, many objectives when we were building a new version of the TLS. So one of the objectives was to fix mistakes in TLS 1.2. So one of the attacks on TLS 1.2 was this thing called triple handshake. So it was band-aided over by a feature called extended master secret. However, in TLS 1.3, extended master secret is actually a core feature of the protocol. You don't need to have this additional negotiation extension for it. If we removed support for weak cipher suites, we also have this forward secrecy with resumption. So TLS 1.3 has a similar thing like Zero Protocol, where it has 1 RTT keys and 0 RTT keys. And you can do Diffie-Hellman exchange to negotiate the 1 RTT keys. So you can get forward secrecy as well with the resumption. It also supports 0 RTT. That goes without saying, otherwise we wouldn't be talking about TLS 1.3 at all. Another thing that TLS 1.3 does is actually simplifies TLS as much as possible. So it's like remove all the complicated features that nobody uses in TLS. Try to, at least. So they completely changed key derivation. So there's this nice ratcheting-based key derivation scheme, which is copied from the specification, really. Completely removed renegotiation. So that was an oft feature that caused a lot of problems in the past with TLS 1.2. And another thing that TLS 1.3 tries to do is to encrypt as much as possible. So it's not really known that in TLS 1.2, client certificates and server certificates are actually sent in the clear. So when people think of client authentication with TLS 1.2 mutual authentication, what you're really doing if you do that over the internet with client certificates which are user identifying, you're actually kind of like violating the privacy of your users because that certificate goes out in the clear. TLS 1.3 fixes this and makes it so that all the certificates, all the handshake messages are even encrypted. So TLS 1.3 looks great. But there are very important differences between TLS 1.3 and 0, why we're trying to move to TLS 1.3 specifically. So one of the core features of TLS 1.3 is that every time the cipher changes, that is, you change from 0 round-trip ciphers to 1 round-trip ciphers, you actually like reset the sequence number. So this might seem subtle, but it's a really important security property where you have complete key separation now between two types of keys. Another thing it does is it explicitly signals the end of early data, so that when my 0RTT data is done, you get a special type of message called end of early data, saying that, hey, my 0RTT data is done. This is important because it avoids truncation-style attacks on 0RTT data. The handshake itself is encrypted, like I mentioned before in TLS 1.3. So handshake keys and application data, the 0RTT data, have different keys completely. So this provides another form of key separation as well. Another important difference is that the 0RTT data in TLS 1.3 is itself authenticated. So the 0RTT keys are used to authenticate the client hello. So this is kind of subtle, like why is this required? Because you exchange not only things like keys, you exchange other information like what is my identity, what is my client identity, what is my cipher suite that I'm negotiating. So there are important things that attackers can fiddle around with. So authenticating the client hello means that an attacker cannot fiddle around with it without being detected at the server. So due to this, TLS 1.3 also does things where the 0RTT mode is not fixed to a Diffie-Hellman key share exchange. You can do symmetric key exchange. You can also do asymmetric key exchange. So it allows you to give you some flexibility in doing both kinds of modes. So it's a little bit more efficient than Zero Protocol as well in that sense. So we're migrating away from Zero Protocol to TLS 1.3. One of the reasons is that it's going to become an IETF standard. So it's really nice to support open standards, and also we'll be able to use TLS 1.3 in multiple places inside our infrastructure and out external traffic as well. It also has these nicer security properties, which we really, really like, and we think that it'll make the internet more safe as well. We've also we've done a bunch of things with Zero Protocol that we've learned some lessons from Zero Protocol, so we've contributed them back to TLS 1.3 as well. So I'll talk a little bit about the lessons we've learned in the next section. And we started implementing our own implementation of TLS 1.3. We call it Fizz. So it's like, this is great. Zero RTT for life. Awesome, YOLO, Zero RTT. We should do Zero RTT everywhere. Obviously, it comes with a catch. So Zero RTT data security model is completely different from 1RTT data. You should be very, very careful when you're using Zero RTT data. The reason is that Zero-RTT data is actually replayable by an attacker infinitely many times if you don't do anything special to prevent it. So for an example, let's take a client is trying to buy a phone from a server, like, I don't know, maybe some phone service. And he sends an encrypted HTTP request, which is sent over Zero-RTT data with the client hello and the other properties that you send initially. Let's say an attacker captures that request. The attacker can actually replay that request ad infinitum to the service and then cause you to buy like 5 phones, I don't know, 10 phones. He could do anything he wants if you don't do anything to prevent that. So obviously, this was a non-idempotent request. So non-idempotent requests are definitely not safe to send over zero-RTT data without any additional protection. You need to protect it against this style of attack. The next question is, like, can you send idempotent requests over zero-RTT data? The answer is no, not without any protection again. So for example, let's say that somebody's using a web browser and he's trying to like request his bank balance from his bank. And the attacker captures the request, the zero-RTT request, and he caches that. So initially, he gets this like bank balance back in an encrypted response. Let's say he captures that, and he keeps replaying this again and again ad infinitum. So he can see, by observing the length of the response, he can see your bank balance, how it changes over time, whether you're making money, whether you're making more money, whether you're making less money than usual, maybe credit reports, I don't know. It's like interesting styles of attacks are possible in zero-RTT data if you do this for any type of request. So it's obvious we need to do something to mitigate these attacks in zero-RTT data. So one of the ways to mitigate this is that we could say that, hey, we're going to cache the zero-RTT client hello that we've seen before and never allow another one to happen again. But in a large multi-server, just multi-geographic distributed server farm infrastructure, it's really hard to maintain a giant distributed cache of all the client hellos that you see. So one of the ways that we found to limit the attack surface of zero-RTT data is to limit the time for which it's valid. So simple idea, it would be that the client sends the time of the zero-RTT data is valid for, and the server checks against that and rejects it if it exceeds the time window. However, implementing it and deploying it is more complex than the idea seems because client clock skew is very inherent. So clients, old mobile phones, or like if you boot up your mobile phone, immediately your battery is dead, your clock skews a lot. So we can't really enforce a tight window of zero-RTT validity time. So we developed a clever solution to this problem where in the first RTT, we actually detect the client clock skew, and the server sends the client back an adjusted clock skew time. And so the next time the client talks to the server, it uses this adjusted clock skew to narrow down the time window that we can validate zero-RTT on. So we contributed this mechanism back to TLS 1.3, and TLS 1.3 uses quite a similar mechanism called ticket age for validating zero-RTT data as well. So once we have this mechanism for limiting time, we still want to restrict the requests that can be used with zero-RTT data as well. We don't want to like allow all requests to be sent over zero-RTT data. That would be catastrophic. So what we have at the end of the day, product teams are really using this APIs that the networking stack provides it. When newsfeed wants to send a request, they use a networking stack API to send a request to get newsfeed. So we wanted to make it simple for them to use zero-RTT data, but not being able to shoot themselves in the foot. That is, they shouldn't do something over and above to get access to zero-RTT data. They should use similar APIs. So we added a new API to our HTTP request API called set replay safety. So if you set replay safety on the request, you're eligible to be sent over zero-RTT data. However, this makes the underlying implementation more complex. Because now the question is, now we know which data is eligible to be sent over zero-RTT and which data cannot be sent over zero-RTT. We need to decide when to send this data over zero-RTT. So network stacks are very, very complex. So what we decided to do was solve this problem at the scheduling layer instead. So the scheduling layer registers a callback with the transport. So the transport is zero protocol or TLS 1.3, the same, it's a transport with these special properties. That is, it's capable of doing zero-RTT. And it will get a callback when it's ready to do zero-RTT, when it's ready to do when it's safe to send 1-RTT data. So the scheduler holds back requests that are not replay safe until the transport tells it it's safe to send 1-RTT data and send it over. So we encountered some fun bugs with this, and meanwhile, it sends replay safe data, zero-RTT, whatever it comes through. We encountered some fun bugs when we first launched this with HTTP 2 stream IDs. So when we held it back, we eagerly assigned the stream ID to the non-replay safe data, and the HTTP 2 semantics have this strict ordering of stream IDs, so we ended up causing errors later. So we had to fix these problems. So there's a bunch of complexities involved with holding back the 0RTT data. You need to make sure you assign stream IDs lazily to HTTP2 streams if you're using this with HTTP2. There's a bunch more of these which I want to talk, which are actually, we have a blog post about, so you can go read about them as well. So next I want to talk about Fizz, which is our in-house implementation of TLS 1.3. With a secure protocol, it's useless to have security without a secure implementation of the protocol. So I wanted to talk about some of the design principles that we've incorporated into Fizz that allow us to prevent us from making logical mistakes affecting the security of our implementation. So it's not perfect, but we've tried to, as much as possible, incorporate good security design principles inside our implementation. So Fizz is an implementation of TLS 1.3. It's written in C++ 14. So it heavily uses smart pointers and unique pointers to prevent memory classes and memory bugs in implementation. So prevent user after freeze, memory leaks, all the good stuff. So we actually currently deployed it to BIP at www.tls13.facebook.com. So you can go access it from any TLS 1.3 capable browser, for instance, Chrome or Firefox, and give us any feedback that you have about it. So as I've said before, we've actually designed it to prevent logical mistakes. So one of the classes of attacks in TLS in the past was state machine attacks. So the TLS state machine is quite complicated. So academics like to refer to it as it is an unbounded state machine with many, many games you can play with it. So for example, in the past, attacks on previous implementations like OpenSSL or like change cipher spec, it's SMAC. So TLS 1.2 has a special message called change cipher spec. OpenSSL had this vulnerability where you could inject this message at any point in the handshake and fix OpenSSL to use 0 keys. So even though the protocol is secure, you would use key 0, so that anybody could decrypt your traffic. So we wanted to avoid these kinds of attacks. So we have instead of having an implicit state machine, we have a very explicit state machine. So you would define your current state, your events that are possible in that state, and your allowed states in the future. Now, once you've defined the entire state machine, we use some clever template metaprogramming to actually, so this is a description of the handler for that state. And we use some clever template metaprogramming to prevent you from even writing code that causes invalid state transitions. So for example, this is an invalid state transition. And so this causes a compiler bug rather than actually causing a runtime error in production when, if we write incorrect code. So this really has prevented a bunch of classes of vulnerabilities in our code. So in the modern TLS world, things like, people have brought it up in past presentations, but things like async crypto offloading or ticket offloading have become very, very common, or doing operations asynchronously have become very, very common. So Fizz is designed with async in mind. So any operation can be made async with the simple future API. So you could just call your async callback function, and the callback function can return a future. Other implementations have to write additional states. That is, you're an async pending state if you were waiting for an async operation. This really complicates the state machine, especially since TLS is a very, very complicated state machine to begin with. So we think this also makes code much safer and makes it easier to write async operations. Another class of attacks on TLS is messages spanning record layers. So you don't want normally messages to span record layers because an attacker could inject a plain text message which would influence your later interpretation of the message. So a class of attacks is the alert attack, for example, on OpenSSL. So the classic misconception on TLS is that TLS encrypts messages. But actually, TLS does not encrypt messages. TLS encrypts records. So a message can span multiple records. So for example, it is perfectly valid for a server hello to be split across multiple TLS records, one of them being, for example, green colored with plain text, and in orange, encrypted with another key. So an attacker, if you allow the server hello to span multiple key changes, an attacker can inject his own server hello to force you to use his own Diffie-Hellman parameters, for instance, and then that would be a vulnerability in the protocol. So instead, past implementations have had these problems. So instead, in Fizz, the whole state is encapsulated in one C++ object. So when we change keys, we throw away the object, and all that state dies with it. So if there's any pending state remaining, it causes an exception and causes the connection to be closed rather than causing a protocol vulnerability in the specification. So we have a bunch of other features. It's designed for mobile in mind, so it runs on ARM, runs on iOS, Android, all the other things. So we've since deployed it to our services as well. So Fizz is interoperable. We found that Fizz is interoperable with Chrome and Firefox so far. And some other implementations as well, with Cloudflare's implementation of TLS 1.3 and a bunch of others. So from our data, we see that 0.1% of Chrome and Firefox traffic are currently coming to us over TLS 1.3. So this is really exciting. Really excited about the next version of the protocol, that it's picking up adoption. What we found was that when we started deploying TLS 1.3 to our services, we started seeing a higher error rate with TLS 1.3 than with TLS 1.2. So one of the reasons we think that this is happening is that we started encrypting the handshake messages and specifically the certificates in TLS 1.3. So middle boxes like inspecting handshake packets a lot. And if you own a middle box as such, please come talk to me. I would love to fix this issue. So what we think is happening is that middle boxes are intolerant to these encrypted certificates, and they're sending errors. They're sending malformed packets to the client, and then clients are considering this a state machine bug, and they're sending us back alerts saying that the connection is closed. This is an invalid packet you sent me. So in the coming month, we have a server rolled out. In the coming months, we're going to roll out a client as well. So this will really allow us to have an end-to-end measurement of how TLS 1.3 and Zero Protocol compare with each other, and so that we can contribute back to the IDF standardization process if there's any issues that we find. So in conclusion, TLS 1.2, it requires a round trip. Round trips suck. Don't do that to your users. Zero Protocol really gave us a useful way to experiment with Zero RTT now, and the abstractions that we built for Zero Protocol and the APIs that we built for Zero Protocol are equally as applicable to TLS 1.3. So when we roll out TLS 1.3, we don't have to rewrite our entire app to be able to roll it out. I would highly recommend, if you own an app, look at TLS 1.3, try to encourage whatever SSL implementation author, SSL implementation library that you use to adopt TLS 1.3, because it's a way to really speed up your application. And be very careful with Zero RTT data as well. I've tried to outline the considerations for Zero RTT data. Be very careful when using Zero RTT data and have an application-level idempotency mechanism at hand. That's all I had. Questions?
Got one in the back right there. You can go ahead.
Hey, so I was wondering what performance differences did you find with using TLS 1.3, especially what is the split up of the ratio of time spent between TCP connection and the SSL itself?
So if I understand your question correctly, you're asking about how much time it takes for TCP versus TLS connection establishment.
Yeah, I know, like a few weeks ago when I tried with Facebook.com with a curl call, it was about 1:3 between TCP and SSL itself.
So it should be 1:1 generally. So there might be some overhead with crypto, but it's really minimal. We try to optimize for ticket resumption as much as possible. So what might be happening is that you might be client constrained in that situation because the full handshake requires an asymmetric crypto operation to happen. So I would try it again with ticket resumption case. So that only requires symmetric crypto, which is much, much faster than asymmetric crypto. Yeah. And, so it should be 1:1. Yeah.
Would it change if I use the TLS 1.3.facebook.com?
It should be the same in both. With TLS 1.2 as well as TLS 1.3. TLS 1.3 it adds a 0 RTT mode on top of 1 RTT, but 1 RTT should be 1 RTT. That is, it should be latency bound rather than being client limited. I think the client might be CPU limited at some point. I'm not exactly sure of your situation, but we can sit down later.
Okay.
Are you using TCP Fast Open?
It's a very good question. So we use TCP Fast Open internally quite aggressively. When we have started investigating, we use it with TLS as well. So when we investigated using TCP Fast Open externally, one of the major blockers is actually happy eyeballs support. So we've had a lot of talk about IPv6 and IPv4. So one of the real interesting situations is that happy eyeballs requires one round trip before you decide whether or not you're gonna use the v6 or v4, right? So really that negates entire optimization of TCP Fast Open, where you make local decisions based on whether or not you are sending the fast open data or not. So what we find is that when we analyze our cache hit rate for happy eyeballs, it is quite low, and I'm not sure whether I can reveal how much that is right now, but it's quite low. And so we're looking at alternative mechanisms to improve that happy eyeballs cache hit rate, so that where we cache whether a network had IPv6 or IPv4, and then you will get an additional boost in speed. The other thing is that really with zero round trip support, TCP Fast Open doesn't give you much over TLS 1.3 zero RTT. The reason is that TCP Fast Open is not streaming. So you have to decide beforehand how much data you're going to send in the zero RTT mode, which is limited to 1 MTU worth of data. And then you send it, and then you wait for the response back. So really, it's a little bit disappointing, but it's complex to play around with, and we don't see that many wins coming from that really, from the TCP Fast Open front. So we've not really invested much into investigating it outside of the data center. But inside data center, we use it quite frequently with TLS, and we see a huge number of wins inside the data center.
Is it? Oh, OK. So outside the data center, have you experimented with both TCP Fast Open versus using TLS 0 RTT?
So TLS 0 RTT will be much faster than TCP Fast Open. Yeah. Okay. Because you are bounded by TLS 1.2. You will have to send only the client hello in the 0 RTT packet. So OK.
OK, cool. Thank you.
Hi. Thanks for the talk. So I was wondering if you've tried Quick, like deploying Quick, and if not, why? What's the main reason?
So Quick is a very fundamental change to infrastructure. We wanted to approach this problem more incrementally. So we are looking at Quick. We're working with the IETF standardization body on Quick. So currently, Quick is a Google proprietary protocol, but the IETF is working on standardizing Quick. The work is moving really fast. So we're really watching that pretty aggressively and kind of participating in the discussions. So that's what we're doing right now. Oh, sorry.
I noticed you mentioned there needs to be like an API call to indicate a request is eligible for 0 RTT. I have to imagine, like in a client like the Facebook client, that's quite a large code base with many API calls, and in each case, the programmer has to understand like the implications of each call, and that seems like a kind of decision that's vulnerable to programmer error in missing cases that would be vulnerable to security issues. How do you address that?
Yeah, so it's a very good question. So how do we, we've tried as much as possible to make every request idempotent in some sort of way as possible, but if you recognize this problem is very similar to the networking problem, where if you have a post request and let's say your network goes down or something, a network error, what are you going to do with the request? Are you going to retry that request, or are you going to keep it not retry that request, really? So what we've tried to do aggressively is to keep track of which requests are actually using 0 RTT and not using 0 RTT, and see whether the list grows, and then audit cases where the 0 RTT request grows. Also, we try to educate people with lint rules and lint warnings whenever they add the new API call, to make sure that they understand exactly what they're doing. So usually what we find is that developers are very, this might seem very counterintuitive, but developers are quite security minded, and when they're doing a new API call, they want to know what the hell does this do? So before they add a new API call. So we're fortunate in that regard as well. But it is a very large code base and auditing but luckily a lot of calls go through a few places. Like there are a few things which, for example, we've released an open source library, GraphQL. So all our feed fetches and stuff happen through GraphQL. So that has already, so people don't directly deal with the networking stack. They express high-level properties of their requests. Like my request is a feed fetch, or my request is an idempotent request. And so there are a few places that we can hook into which cover a vast majority of cases rather than covering every single case. Yeah.
Hi, my name is Vasant. Thanks for the talk. I have a question that do you know of existing man-in-the-middle proxies for TLS 1.3? Because these days, lot of enterprises breaks TLS 1.1 and 1.2 on almost all the sites. I know that TLS 1.3, it is relatively hard to build proxies like that. So do you know any existing TLS 1.3 proxies?
I unfortunately don't, and I don't know whether I should advertise for any, even if I did know. But I don't know of any. I don't know of any proxies as such. Yeah.
Thanks.
Much so.